Welcome to the another class of design of RC structure. In this lecture, we are going to design a two-way slab with the help of limit state method. In previous lecture of one-way slab, I have already discussed about the analysis of slab, about the conditions to know which slab have to design as one way and which type of slab have to design as two-way. As per IS 456-2000 consideration, we know if the ratio of longer span and shorter span is less than 2, then we have to design the slab as two-way slab, as I have discussed in previous video. So in this video, I am going to design two-way slab directly. So let's read out the problem first. Design a RC slab for a room of clear dimension 4 meter by 5 meter. The slab is supported on walls of width 300 mm. The slab is carrying a live load of 4 kN per meter square and floor finish 1 kN per meter square. Use M20 concrete and Fe 415 steel. The corners of slabs are held down. So before starting the problem, I am going to discuss the basic part of two-way slab. We know that in two-way slab, bending comes in both sides. So we have to design reinforcement for longer span and shorter span both. There are no such as distribution bar. There are a torsional moment come in the corners. So in corner there are torsional reinforcement have to be designed, and for both side, that means for longer span and shorter span, we have to design reinforcement for middle strip only, and for 4 edges we have to provide edge strip as per IS 456-2000. The total consideration of two-way slab is given in Annex D of IS 456-2000. So let's have a look to Annex D IS 456-2000. This is Annex D of IS 456-2000. Slab spanning in two directions. So these are the consideration. We will read it out when we will solve the problem. That will be easier to you to understand the clause and the consideration. There are two figures also. In page number 90, we can find this of IS 456-2000, and next page, table 26 also needed for this design. So let's start to solve the problem. Ly by Lx is equals to 5 meter by 4 meter. Ly is longer span, that is 5 meter given in question, and Lx is shorter span, that is 4 meter, that is also given in question. That is equals to 1.25. So this is less than 2. That means this is a two-way slab. We have to design the slab as two-way slab. Let's assume L by D, length to depth ratio, is 25. From this assumption, small d effective depth is 4000 by 25, that is 160 mm. Now assuming clear cover as 15 mm and using 8 mm main bar, so overall depth will be effective depth as per assumption, that is 160, plus clear cover, that is 15, plus half the diameter of main reinforcement bar, that is 4. So overall depth is 179 mm, or we can say 180 mm. Now effective depth is equal to overall depth 180 minus clear cover plus half dia, that means 15 plus 8 by 2 is 4, that is equals to 161 mm. Next step is span consideration. As two spans of two-way slab is in consideration, so we have to find out effective span in x direction as well as in y direction also. But we have to consider effective span as per clause number 22.2 of IS 456/2000. Look, simply supported beam or slab, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of the slab or beam, or center to center of support, whichever is less. So as per clause, the effective span in x direction, either center to center distance, that is equals to 4 meter, the clear span of length of shorter span, plus 0.3. This 0.3 meter, that means 300 mm, is the width of wall, that means width of support, which is given in question. So that is equals to 4.3 meter, or clear span plus effective depth. So clear span is 4 plus effective depth as per calculation is 0.161 meter. So that is equals to 4.161 meter. From these two, the shorter, the lesser will be accepted. Therefore, effective span is equals to least of the above, that is equals to 4.161 meter. Similarly, the effective span in y direction, Ly, is equals to 5.161 meter. So now we have to design the load, which is denoted by WU, U for ultimate. So self weight of slab is equals to 0.18 into 1 into 25, that is 4.5 kilonewton per meter. 0.18 means 180 mm, the overall depth we have considered, multiplied by 1. 1 is, we know slab is always designed as 1 meter width of beam, and 25 is unit weight of RCC. So self weight of the slab is 4.5 kilonewton per meter. Floor finish load is given 1 kilonewton per meter. Now floor finish load is given 1 kilonewton per meter square in question. So 1 into 1, that is equals to 1 kilonewton per meter. Now live load is given 4 kilonewton per meter square in question. So live load is 4 into 1, that is 4 kilonewton per meter. This one multiplied with finishing load and live load is 1 meter width, which is in consideration. So total load will be 9.5 kilonewton per meter. Now we have to multiply load factor, that means partial safety factor for load, the combination of dead load and live load, which is we can get from table 18 of IS 456/2000, that is 1.5 for the combination of dead load and live load. So factored load will be 9.5 into 1.5, that is equals to 14.25 kilonewton per meter. This is factored load. So next step is design moment and shear. For this step, first of all, we have to get the knowledge of Annex D IS 456 2000. So let's check it out. So where is Annex D of IS 456 2000? As per clause number D11, the maximum bending moments per unit width in a slab are given by the following equations. Mx for shorter span is equals to alpha x w Lx square, and my moment for longer span is equals to alpha y w Lx square, where alpha x and alpha y are coefficients given in table number 26. We will just go through table number 26 after this. W is total design load per unit area. Mx and My moments on strips of unit width spanning Lx and Ly respectively, and Lx and Ly is effective lengths of shorter span and longer span respectively. So let's check table number 26. So formula for moment in shorter span Mx is equals to alpha x w Lx square, and for longer span My is alpha y w Lx square. Let's check table number 26. So table number 26 is bending moment coefficient for rectangular panel supported on 4 sides with provision for torsion at corners. So table number 26 is given for bending moment coefficient for rectangular panels supported on 4 sides with provision for torsion at corners. In the table, in most left column, number 1 case number is given. Then second one from the left is type of panel and moment considered. So there in this column the support conditions are given. As per support condition, coefficient of moment will change. There are total 9 types of support system. In next column, short span coefficient, that is alpha x. There are few values of Ly by Lx. Depending upon the value, the ratio of Ly Lx, the value of alpha x will change. And in last column from the left, that is long span moment coefficient, that is alpha y, for all values. The alpha Ly Lx value is not the criteria for this, only support condition is the criteria. So these values are given for these support conditions. So there are many support conditions like interior panels, one short edge continuous, one long edge discontinuous, two adjacent edges discontinuous, two short edge discontinuous, two long edge discontinuous, three edge discontinuous, four edge discontinuous, etc. If any condition among these is directly or indirectly given in question, we will go through these values depending upon Ly Lx value. If any condition not given in question, we have to consider any condition among these 9 conditions. Okay. So generally we consider, if not given, if support condition is not given in question, generally we consider the number 9 4 edge is discontinuous. Okay, so let's go to the problem. So in this case, support condition is not given in question. So we may consider the slab is supported on all the 4 sides and its corners are held down as given in question. Therefore, we have to consider, as per table number 26 of IS 456/2000, for Ly by Lx value is 1.25. So let's check 1.25 value for Ly by Lx is given or not. If not given, it definitely lies between any two values, then we have to interpolate this. So let's check first from table number 26. Now look at table number 26, the support condition is number 9, 4 edge discontinuous. So our value for Ly by Lx is 1.25. Now look, 1.25 is not given in this table, but 1, 1.1, 1.2, 1.3, 1.4 these are given. So 1.25 is lies between 1.2 and 1.3, that is column number 5 and 6. So values are definitely between this. So column number 4 and 5, sorry 5 and 6, column number from 5 and 6, the for 1.2 alpha x is 0.072 and for 1.3 alpha x is 0.079. So definitely for 1.25 the value of alpha x lies between 0.072 and 0.079. Now we have to interpolate this to find out the value, and for Ly, look, this is given 0.056. Now we have to interpolate. So for alpha x, we have to find out the values between 0.072 and 0.079. So as per formula of interpolation, 0.072 plus 0.079 minus 0.072 by 1.3 minus 1.2 multiplied by 1.25 minus 1.2, that is equals to 0.075. So value of alpha x is 0.075 and value of alpha y is 0.056. That is also given in the last column of table number 26. Okay. So moment in shorter direction mu x is equals to alpha x w Lx square, that is equals to 0.075 into 14.25 into 4.161 square, that is equals to 18.5 kilonewton meter, and moment in longer span mu y is equals to alpha y w Lx square, that is equals to 0.056 into 14.25 into 4.161 square, that is equals to 13.8 kilonewton meter. Now we have to find out maximum shear force, that is Vu equals to W into Ly by 2. Now we have to find out the maximum shear force value, that is Vu equals to W into Ly by 2, that is equals to 14.25 into 5.161 by 2, that is equals to 36.77 kilonewton. Now next step is minimum depth required. So from the formula of Annex G, we may write mu is equals to 0.36 into xu max by d within bracket 1 minus 0.42 xu max by d bracket closed b into d square into fck. So mu, that means limiting moment. So here the limiting moment is 18.5 into 10 to the power 6 as we calculated earlier is equals to 0.36 into xu max by d is 0.48 regarding the condition. The value of xu max by d we may find out just below clause number 38, and in this question Fe is 415, that's why xu max by d is 0.48, as per IS 456 2000. Within bracket 1 minus 0.42 into 0.48, bracket closed. Now B is the width, and that is 1000 into D square into FCK is 20 here. So from this, D required is equals to 82 mm, which is less than depth which we have considered. Hence it's okay. That means the depth of the section which we provided, that is greater than required depth. That means the section is safe regarding depth consideration. So now Annex D of IS 456 2000, as per clause number D 1.2, slabs are considered as divided in each direction into middle strip and edge strips as shown in figure 25. This is figure 25. So for reinforcement arrangement, in middle portion middle strips are given, and in edge portion edge strips reinforcement are given. So as per clause, the middle strip being 3/4, that means 3/4 of the width, and each edge strip is 1/8 of the width. Look, for span LX, 3/4 of LY is middle strip and LY by 8 per edge strip, and for span LY, middle strip is 3/4 of LX and edge strip is LX by 8. So now let's go to the solution. Look, here in the calculation of design of main reinforcement, as per IS code provision which we have read just, the calculation has been done. So along shorter span, that means X direction, middle strip is width of middle strip is equals to 3/4 of LY, that is equals to 3/4 into 5.161, that is equals to 3.9 meter, and D is 161 mm. Now as per the equation of Annex G of IS 456 2000, to find out moment, ultimate moment, the formula is mu is equals to 0.87 Fy into AST into D within bracket 1 minus AST Fy over B into D into FCK. So in this equation, our known values are: mu is our known value, moment, that is our known value, Fy is grade of steel, the yield strength of steel is our known value. Now AST means area of steel, so area of steel is unknown here. We have to find out area of steel from this equation into D, that is depth, that is also known value, within bracket 1 minus AST area of steel, which we have to find out is unknown value, then Fy grade of steel value is known, by B is width, D is depth, and FCK is characteristic strength of concrete. All are known values. So now we have to just put the values in equation, and from this equation we can find out the unknown value of AST. So after putting these all values, you can see here 18.5 into 10 to the power 6 is equals to 0.87 into 415 into AST into 161 within bracket 1 minus AST into 415 by 1000 into 161 into 20. From this equation we may find out the value of AST. So value of AST is equals to, as per calculation, 332.5 mm square. Okay. So now using 8 mm dia bars, that means area of cross section of one bar is pi by 4 into d square, that means pi by 4 into 8 square, d here is diameter of bar, that is equals to 50.3 mm square. So spacing will be equals to 50.3 by 332.5, that is AST, into 1000, that is equals to 151 mm, or we may use the spacing 150 mm. So as per clause, spacing should be least of 3 into depth 3d, that is 3 into 161, that is equals to 483, or 300 mm, or which we have calculated, that is 150 mm. So among these three least value is 150 mm, so spacing should be 150 mm, center to center will be provided. Now area of steel minimum is 0.12 by 100 into B into D. This is HYSD bar, that's why 0.12 value is used, that is equals to 0.12 into 1000 into 180 by 100 into 216 mm square. Now our AST provided, which amount of area of steel we have provided, that is 1000 into 50.3 by 150, that is equals to 335 mm square, which is greater than the value of AST minimum, that is 216 mm square, hence okay. So provide 8 mm dia bar at the rate of 150 mm center to center in the middle strip of the width 3.9 meter, right? So after all calculation done in the drawing, we can see the middle strip, how it's distributed. Okay, now along longer span, y direction, middle strip, width of middle strip is equals to 3/4 of Lx, that means 3 by 4 into 4.16, that is equals to 3.12 meter. Now effective depth along y direction will be d minus 161 minus 8, that is the diameter of bar, because already bar along x direction is provided. So in when y direction span is in consideration, so definitely dia of one bar through x direction which is provided definitely will be deducted. So that's why diameter of bar 8 is deducted from effective depth. Okay, so depth for y direction is 153 mm. Now mu, again same formula, same approach from NXG. Mu is equals to 0.87 Fy AST into D into 1 minus AST into Fy over B into D into FCK, bracket closed. Here also only area of steel AST value is unknown, other all values unknown. So just put the values. Mu is 13.81 into 10 to the power 6, that is equals to 0.87 into 415 into AST into 153, within bracket 1 minus AST into 415 over 1000 into 153 into 20. So all these values are known, only AST unknown, and mu is calculated earlier in this solution. So from this equation, area of steel will be 261 mm square, that is greater than AST minimum, so hence okay for design. So spacing of 8 mm dia bars in 50.3 into 1000 by 261, that is equals to 192 mm, or we may write that is equivalent to 190 mm. So In this case also definitely 190 will be the lesser value among the 3D and 300 which is the spacing values. We have to consider the least value as earlier. So 190 will be the definitely least value. Therefore, provide 8 dia bars at the rate of 190 center to center in the middle strip of width 3.12 meter. Okay. So next step is reinforcement in H strip. So we know we have calculated earlier that AST minimum, area of steel minimum, is equals to 216 square. Now using 8 dia bars, the spacing will be 1000 into 50.3 by 216, that is equals to 232 Now for spacing will be list of the following: 5D, 450 and 232 which is calculated. So spacing should be 232 or we can use 230 Okay. So in each strip we calculated just like distribution bar of one way slab. AST minimum is enough reinforcement for each strip. Okay, so we took area of steel as AST minimum, and spacing consideration is also like distribution bar of one way slab. That's why the spacing amount will be list of these followings, slightly different than the main reinforcement. Okay, so now using 8 dia bars at the rate of 230 center to center in the H strip of width half into 5.16 minus 3.9, that is equals to 1.04 meter along x direction, and H strip of width half into 4.16 minus 3.12, that is equals to 0.52 meter along y direction. In this case we use half because from the full effective span, if we deduct middle strip, we will get total length of H strip from both sides. But here we have to for reinforcement, providing reinforcement and design, we have to know the one side of H strip. That's why we have just multiply the half value with this to get one direction, only H strip, one H strip. Okay, now next step is check for shear. This is in common format. Nominal shear stress tau V is equals to VU by BD. Shear we have calculated earlier. So VU is 36,770 by 1000 into 153, that is equals to 0.24 Newton per square. Percentage of steel AST by BD into 100, we know this formula. So AST is 335 by B is 1000 and D is 161 into 100, that is equals to 0.21%. Now for percentage of steel 0.21% and M20 grade concrete, we have to find out the value of tau C from table number 19 of IS 456 2000. So let's check the table number 19. So table number 19, design shear strength of concrete, tau C in unit is Newton per square. So now in left column 100 AST by BD, percentage of steel, 0.21 is not in the list, but 0.21 is lies between 0.15 and 0.25. Now for M20 grade of concrete, percentage of steel, if 0.15, then the tau C value is 0.28, and for 0.25 the value is 0.36. that means for 0.21 is definitely lies between this 0.28 and 0.36. We have to interpolate that. So now we have to interpolate. Now tau c is equals to 0.28 plus 0.36 minus 0.28 over 0.25 minus 0.15 multiplied by within bracket 0.21 minus 0.15. The value will be 0.33. So the tau c value is 0.33. Now for 180 mm thickness of slab, value of K coefficient is 1.24, which you can find out from clause number 40.2.1.1 of IS 456-2000, page number 72. I have already showed in last video for one-way slab that page. Clause number is written here, you can easily find out there. So K value is 1.24. So K tau c is equals to 0.33 into 1.2, that is equals to 0.41, which is greater than tau v. That means no shear reinforcement is required because there are no excess shear. Okay. Now next step is check for deflection. So for this, first of all we have to find out modification factor from IS 456-2000 figure 4. That modification factor will be multiplied with length to depth ratio, right? So percentage of steel is 0.21, we know. Now Fs, this formula is given just below figure 4 of IS 456-2000, 0.58 into Fy, AST required by AST provided, that is equals to 0.58 into Fy is 415 within bracket, AST required is 333 by provided is 349, that is equals to 240 Newton per mm square. So we have to find out modification factor for percentage of steel 0.21 and Fs 240 MPa. So let's check figure 4 of IS 456-2000. So this is figure 4 of IS 456-2000, Fs is 240 and percentage of steel is 0.21. So from this two we may find out the approximate value of modification factor. So modification factor is almost 1.6. For simply supported beam, L/G max is equals to 20 into modification factor 1.6, that is equals to 32, and length to depth ratio provided, L/G provided, is equals to 4161 by 161, that is equals to 26. So this value is lesser than the maximum value, hence it is okay. So next step is torsional reinforcement at corners. In case of two-way slab, in every corner torsional reinforcement or corner reinforcement have to provide to resist torsional moment which comes in two-way slab. So as per IS code consideration, mesh size is Lx by 5, that is equals to 4.16 by 5, that is equals to 0.832 meter, which is equivalent to 840 mm. Now area of torsional reinforcement is 3/4, that means 3 by 4 of 332.5, that is equals to 250 mm square. Now using 8 mm dia bars, dia of 1 bar we know 50.3, so spacing is 50.3 by 250 into 1000, that is equals to 201 mm, or you can say 200 mm. So provide 8 mm mesh of bars at 200 mm center to center in a mesh. Now design part and reinforcement part is complete. Now time to arrange reinforcement, okay, before the drawing. So before starting this arrangement consideration, just check out once the IS code provision about this arrangement. Now look, as per IS code provision, Annex D of IS 456 2000, clause number D 1.4, tension reinforcement provided at midspan in the middle strip shall exceed in the lower part of the slab to within 0.25 L of a continuous edge or 0.15 L of a discontinuous edge. So depend upon this edge condition. Now, as per code provision, the reinforcement arrangement. First, on the bending half of the main bars at a distance 0.15 Lx, that is equals to 0.65 meter from the center of support, or 650 minus 150, that is 500 mm from edge of support along x direction. Available length of bars at top 650 minus 130, that is equals to 520 mm from center of support. Now next part is bending half the main bars at a distance 0.15 ly, that is 775 mm from center of support, or 775 minus 150, that is 625 mm from edge of support along y direction. Available length of bars at top 775 minus 130, that is equals to 645 mm from center of support. So regarding this reinforcement arrangement, we have to draw the figures. So this is a longitudinal section of short span. So you may see here the drawing. From drawing you can understand the overall length, the effective length, everything, and the distance of bent up bar. Okay, everything is written in drawing. Now next drawing is along long span. The span length change as per our question and as per our calculation. So this is the length and distance of bent up bar, lower portion and upper portion. Okay, so this is the drawing. Next part is plan of bottom reinforcement. Okay, so here everything is given: middle strip, edge strip and corner reinforcement. This is the main plan of bottom reinforcement, which we have mainly designed, which you have get through the design. As per the design, this drawing has been done. You can see here the mesh size, edge strip size, number of dia of bar at given support. So this is another view which is of top reinforcement. Here edge strip and mesh are given, but middle strip is not given. And this is the main drawing. So here the problem is end. Thank you.